Okay, thanks a lot, Katerina, for the invitation. And so basically, yes, so I'm gonna talk about magic angle bilayer graphene. And in particular, as you asked me, I'll go with a thorough introduction of the field. And then, as you will see, so many of the observations we did in transport are also very similar observations. Ali will talk next in STM, and basically I'll try to make a very thorough introduction of the field also for the speakers to come. So before I start, let me just thank my group. So all of the work which I'm going to present was done by several key people like Xiaobo Lu, Ipsitedas, Peter Stepanov, and Paul Seifert in my group. And in particular, we're also thankful for great theory collaborations, which allowed us to interpret all our results, in particular Andrei Bernovic, Alan McDonald, Leonid EFETOV. And I also want to thank some scanning probe groups, which we're also collaborating with, like Elizeldov, Felix Baumberger, and Milan Allen. And just to really give sort of the introduction to the field. So basically the field of graphene is, of course, already much longer in existence. So since 2004, people have realized that they can extract a few layers out of bulk crystals. And actually, when I joined the field in my PhD work in Philip Kim's group, we were basically all surprised that actually in graphene research, there's not so much physics like electronic interactions going on. However, back then, in around 2007, there were already a lot of initial predictions how to make graphene interacting, how to make graphene superconducting, for example. And in Philip's group, I spent considerable amount of time on this avenue. However, many of these approaches didn't work for normal graphene. However, the breakthrough then came with Pablo Carrero 2 years ago, who basically introduced a novel type of graphene called twisted bilayer graphene. And he showed that really in this type of graphene, correlations can be strong, and he observed correlated insulators. And side by side, and in those two papers, he also reported on superconductivity in these devices. And if this would not be enough, also in the following year, many groups started observing magnetism, in particular David Goldhaber-Gordon, and also in the group of Santa Barbara, they have shown that these magnetic states can also give rise to topological edge states, and they observed the anomalous quantum Hall effect. So overall, we have here in one materials platform really a lot of modern quantum metaphysics combined into one materials platform. And these phases, as I will show, they are actually existing in one device. They can be gate tunable between one another. They can also be switched from one to another by applying magnetic fields. And really, I think we're just in the beginning of the understanding of what gives rise to these phases and what is basically next to come after that. And so the outline of my talk is really just, again, a broader introduction of the physics of twisted bilayer graphene. Then I will talk about some transport results from my group, where we basically observed all of these phases, like superconductors, correlated insulators, magnets, and charge insulators. And maybe if time allows, I'll talk a little bit about applications where we actually also make quantum sensors out of this class of materials. Okay, so again, very slow introduction for everybody who's maybe not familiar with van der Waals materials and twisted bilayer graphene. So again, the field really started in 2004 when the people from Manchester, like Andrei Gaim and Kostya Novoselov, they were able to show that they can extract single layers, single atomic crystals from bulk van der Waals materials. In this case, graphene was extracted from bulk graphite flakes. And so these two-dimensional materials can be extracted onto silicon oxide platforms. And by now, we have actually observed many more of these two-dimensional materials, and they cover basically every class of quantum matter system, from topological insulators to magnets to superconductors and so on. And so this is one part of the game, and the other part of the game was that also people around 2010, 2013, specifically at Columbia, in the group of Philip Kim and Corey Dean and Jim Hone, they also discovered that actually you can now take different material species and you can actually assemble them in the third dimension, one on top of another. And this process is demonstrated here. So, for example, with hexagonal boron nitride flakes, one can, through the stamping technique, one can pick up graphene layers and repeat this trick many, many times. And one can basically assemble layers on top of layers of two-dimensional materials. And one can basically define the sequence and the orientation at which these layers are deposited on top of another. And you can really go and assemble any kind of combination of superconductors, ferromagnets, Dirac materials, etc., one on top of another, and create your designer crystals. And I think the main surprising thing in this direction was that actually all of this works with these simple techniques. So really early transmission electron microscopy studies really showed that the interfaces between these so-assembled materials are extremely good. So here in HDN, graphene, and MOS2, you basically see ultra-clean crystallographic interfaces between the different layers. And really, you can always find very well hybridized systems. And of course, the center of the talk here is also that in these materials now, you can also orient the twist angle freely, and you can create these Moiré super-lattices, which I will talk a little bit, talk in more detail in a second. And I really, before doing that, I really want to contrast how really special these Moiré super-lattices are, because actually heterostructures is nothing new. So people have tried to make heterostructures for like decades now. And they came up with really complicated techniques, for example, like molecular beam epitaxy to assemble layers of different species, one on top of another. And so these techniques predominantly are based on the principle that you can sprinkle single atoms onto surfaces, and atom by atom, you can assemble layers. And when you change the atomic species, then you can assemble a different species of atomic layers, one on top of another. However, because you start with single atoms, these layers assemble on the given crystallographic orientation, which they inherit from the underlying parent substrate. And therefore, all layers grow in the same crystallographic orientation, and really the crystallographic orientation is locked. And this is really different in van der Waals materials, because here we don't start with single atoms, but we already start with preformed two-dimensional lattices. Therefore, we can really stamp layers of these materials with any given crystallographic orientation. We can orient them really in the direction we like. And so in the example of bilayer graphene, the way these Moiré super-lattices work is the following. So first of all, of course, we start with just a graphene lattice, which is just given by this hexagonally arranged carbon atoms. We can define two sublattice sites, A and B, and we can also define a hopping term gamma 0 between these. And if we do the tight binding calculation and the low energy approximation of this, we can find that the band structure of these materials of graphene is given by this Dirac dispersion relation. And basically, this was the famous claim that electrons in graphene behave like massless particles, and the dispersion relation is really linear. And up front, also in graphene, of course, the hexagonal, the Brilliant zone is also hexagonal. And we have actually two of those Dirac cones in the K and K prime points. And therefore, in graphene, typically we have a fourfold degeneracy. So we have valleys and we have spins. Okay, so the story is very similar when we now take AB bilayer graphene. So this is the naturally occurring sort of the stable form of bilayer graphene is AB stacking, where actually the top layer is slightly shifted with respect to the bottom layer. And because we now have 4 electrons per unit cell, we have now 4 bands. And because now we have many additional hopping terms between the layers itself, also the dispersion relations becomes renormalized, and we get, instead of linear dispersion relation, we get this hyperbolic dispersion relation, which is almost quadratic at zero energy. And of course, all these hopping terms get mixed up when we start changing the orientation of the crystal. So this is what happens if we twist one layer on top of another. as you can see, so the superimposed there's a superimposed potential on between the two layers, which is basically defined by just this geometric interference between top and bottom layer. And this lattice is called the Moiré super-lattice. And as you can see, so for very small twist angles, which we typically deal with, so for example, the magic angle, as I will show later on, is 1.1 degrees. We get an extremely large superpotential with a lattice constant of 14 nanometers. And if you count up the electrons in one unit cell, it's about 10,000 atoms. So it's an extremely large supercell. And the way we approximate it is really by approximating AA stacked regions and AB and BA stacked regions, which are kind of oscillating in real space. And these AA lattice regions are basically where the two layers, top and bottom layer, are exactly one on top of another. And AB is again where the top and bottom layer are slightly shifted. And of course, these things were observed in experiments. So most prominently, of course, in Ali Yazdani's group, as he will show later on, all of the important work was done there, and also the groups of Caltech, Columbia, and Rutgers. So there was many STM work, and really, when you probe the topography of these type of devices, you can really resolve these AA lattice sites. And sort of this image, which I'm showing here, this really doesn't show single atoms, but it really shows the Moiré superpotential. And of course, as I mentioned, of course, the hopping terms also between the two layers are oscillating in real space. They're not well defined for the entire lattice. Also, of course, the band structure becomes reconstructed. And actually here shows band structure calculation for for twisted bilayer graphene with a twist angle of 1.3 degrees. And as you can see, so it kind of resembles the band structure of AB bilayer graphene with those two bands here at higher energy. But what really dramatically happens is that around zero energy, the band structure becomes strongly renormalized. In particular, you're getting close to zero energy. You're getting these flat bands, which basically the flatness of the bands results in extremely high density of states, and this density of states, of course, then makes the the flatness of the band makes also, of course, the kinetic energy almost vanishing, and because the electrons almost stop moving, then interaction terms start dominating the whole structure. And as you can see, so in recent ARPAS experiments led by the Felix Baumberger group, actually these things are also observed in these ARPAS experiments. So of course, everything is smeared and blurry in ARPAS experiments, but nevertheless, we clearly observe these flat bands, and we clearly observe the band gaps which are also formed in the system. Okay, so. And basically, for the rest of the talk, I'll be basically dealing with the following system. So I will be dealing with a band structure which looks like that, where we have for magic bilayer graphene, where we have these isolated flat bands formed at around zero energy. They're extremely flat, so they're only their bandwidth is in the order of 10 MeV. And because of corrugation and strain effects, also, band gaps are formed, which isolate these flat bands to the higher order bands. And in addition, as I will also mention later on, also people like Andre Bernovic and many others have also analyzed these bands for their topological nature. And they have revealed that really these mini brilliant zones which are formed, they basically have a non-zero helicity of 2 instead of 0, like a normal graphene, and therefore there are many theories out there that predict that actually the flat bands have to be thought as of Chern bands, because one cannot easily define a localized Wannier function for this problem. And as I will later show on, we really see also these signatures of topological transport in these devices. Okay, so first of all, let me then switch towards the transport measurements in our devices, and in particular, let me introduce the devices, how we make them. So the typical devices are made in this encapsulated form, where they're encapsulated in hexagonal boron nitride layers. These layers are just insulators for what we are concerned. And typically underneath such a HBM layer, we also have graphite layers. And in this sort of approximation, we can treat graphite just as a normal metal. And as I will, and basically what we can do with this graphite are many things, but first and foremost, we can just apply a voltage to this graphite. And via the capacitance between the graphite and the twisted bilayer graphene, we can actually tune the carrier concentration in twisted bilayer. And the capacitance is strong enough that we can really empty and completely fill these flat Moiré bands. And the other thing I want to say that really making homogeneous devices is a real challenge, because if you actually think of the mechanical properties of graphene, it is really most accurately compared to this run wrap with which you wrap your sandwich. And so it's really not a rigid, it's really rather this floppy material, which is elastic, and you can easily make folds, and you can trap bubbles when you assemble two layers of this run wrap, one on top of another. So really the main challenge in the fabrication of these devices is keeping these devices bubble free and without any folds. And so right now, probably the best devices which we ever made can be homogeneous can be relatively homogeneous, where the inhomogeneity of the twist angle is only 0.01 degrees over like a length scale of 10 micrometers. But these are really exceptional devices. Most of the time, we are still struggling with inhomogeneities. Okay, so and in transport, really what we measure is just resistance as a function of carrier density. So we really just monitor the four-terminal resistance while we sweep the Fermi energy through the Moiré band, and we start basically in this gap here. Of course, in this gap is this position here, and you can see the resistance is extremely high. It's in the orders of mega ohms, and really this position here marks this band gap here. Then if we sweep through this direction, we basically sweep the Fermi energy through the band and into the higher order band gap again. And therefore this position here, again, this is a band insulator, and this marks this energy gap. So at center, at zero energy exactly, we observe the charge neutrality point. So this is just where the valence and conduction Moiré bands touch. And so all of those things which I just mentioned, they are explained by the single particle picture. What, however, is not explained by the single particle picture is all the other features which we observe here. And namely, those are in particular these resistive states at exactly 1 electron per unit cell, 2 electrons per unit cell, and 3 electrons per unit cell. And the same things happens actually for holes for -1, -2, and -3 electrons per unit cell. And so the ongoing understanding now of these states is, and I will explain much more in the end. So of course now we also understand these states more, taking those topological states into account. But sort of the first order approximation which people started thinking about this problem was really just a Mott insulator picture, where basically we can define the kinetic terms and the Coulomb terms in the problem, and we can just assume electrons occupying different lattice sites and being allowed to hop in between the lattice sites. And so, of course, when we have a full occupation of electrons and the unit cells are all occupied with an integer number of electrons, it is not favorable for electrons to hop between the lattice sites, because every time many electrons are occupied in one lattice site, it costs additional Coulomb energy. So therefore, for a situation where the Coulomb energy is extremely high and the kinetic energy is relatively slow, so this is this criteria that U versus T is much bigger than 1, then it is favorable for the system to just localize the electrons in each lattice site and to form, therefore, insulating state. which is really formed just due to this Coulomb interaction. And as we'll later show in more detail, really since we have spin and Bell degeneracy in the system, and we basically have SU4 symmetry of the flavors, we can really form different gaps at 0, 1, 2, and 3 electrons per unit cell. And really, as this sort of picture kind of hints already, every time we form one of those gaps, some symmetries must be broken. So if we have 1 electron per unit cell, we can have a situation where, for example, the valley degrees of freedoms are broken, or the spin degrees of freedom are broken. And in a broader term, since we have SU4 symmetry, of course, any sort of combination in this phase space is possible. Okay, so the other thing, of course, which was also seen in the early transport measurements, is that indeed the system not only shows these correlated insulators, but it also shows superconductors. So this is basically the same data which I showed before, and really this is now a color plot taking also the temperature dependence into account and the y-axis here. And so red regions are the insulating regions, whereas the blue regions are now the regions with zero resistance. And as you can see, so the superconducting domes are formed in between the correlated insulator states, and these superconducting domes basically can appear in many places of the phase diagram, but predominantly they're appearing close to the correlated insulators. So, and to just also highlight how we are sure that these phases are really superconductors. So of course we have made many tests. So of course, first and foremost, we observe a resistance versus temperature dependence, which shows a clear critical transition temperature where the resistance drops to 0. Then of course, in magnetic field, we can sort of kill the superconductor where the critical magnetic field as a temperature behaves as predicted by the Ginzburg-Lambda theory. We see, of course, a critical current in the nonlinear conductance measurements. And I think so far, really the most striking evidence for the superconducting states is the Fraunhofer interference pattern, which originally many groups have reported, and it is believed that there's Josephson junction formation in the system because of some phase separation, and this phase separation is believed to be disorder-induced. However, basically last week there were several papers by, again, Pablo and by the Ensling group, which also showed that these Josephson junctions can be prepared in a gate-tunable way. So really, this Josephson effect is very robust in the system and can be controlled by local gating. And so the thing I want to mention about these superconducting states is really that immediately after the discovery of these superconducting regions by Pablo Ferrero, there was a huge debate of whether these superconductors are unconventional. And the thing is, they're indeed unconventional in the sense that they're very unusual. So they have several properties which are really strikingly different than in other superconductors. So first of all, this is a diagram which shows different superconductors as a function of their thickness. So how thin can you prepare them, and as a function of carrier density per sheet. And as you can see, magic graphene is the thinnest superconductors you can prepare, and B, it is a superconductor which with extremely low carrier density. So compared to normal superconductors, which are BCS-like, like aluminum or niobium, the carrier density in twisted bilayer is 4 to 5 orders of magnitude lower. And also even compared with high temperature superconductors like BISCO, the carrier density is still 3 orders of magnitude lower. So I think the first excitement about the superconducting state was really, how can such a low carrier density system have still a sizable TC? So TC here is still in the orders of 5 Kelvin now. And really, if you compare sort of the coupling strength and you sort of look at the ratio between the critical temperature and the Fermi temperature, then really it's only comparable to the high temperature superconductors. And of course, also the initial sort of excitement was related also to the analogy to the cuprates, where again, we seem to have a magic angle graphene, we seem to have a system which has strong correlations, and at the same time, it behaves like a superconductor. And actually, if one sort of now naively looks at the phase diagram of the cuprates, where you have this parent Mott state, which upon doping becomes a superconductor, then actually in graphene you can kind of paint the same picture, where you can start from a correlated insulator, and upon doping it becomes a superconducting state. So we were now particularly interested in this relation between the correlated insulators and the superconductors, and we tried to make a control experiment. So basically, what we tried to do is we tried to control the strength of the correlated insulator. And the intuition was that really you can strongly control this correlated insulator strength with several parameters. So first of all, because we can't control the kinetic energy in the problem, so T is really just a function of twist angle. So as I mentioned before, if we look at the dispersion relation, the bandwidth is lowest at around twist angle of 1.1 degrees. However, if you go slightly away from this magic angle, the bandwidth becomes slightly broader, and therefore T becomes bigger. So you can actually control the kinetic energy by tuning T, by tuning theta, by tuning the twist angle. And the other tuning knob and the problem is that actually, as I mentioned, our device is in this complicated dielectric environment. And actually, with changing the dielectric environment, you can actually control U, you can control the Coulomb energy. So therefore, we thought it's possible that actually you can control this U versus T ratio, and maybe it's possible that you can strongly manipulate the correlated insulator strength. And so, in particular, talking about the dielectric environment, we realized that actually what could be a crucial ingredient here is really this metallic graphite gate, which is very close by to our twisted bilayer graphene. And so we collaborated with Leonid EFETOV, who actually calculated for us what is the critical length between this graphite gate and the magic angle graphene for screening charges in the graphite to really strongly affect the interactions in the magic graphene. And we found actually that the length scale of the problem is similar to the size of the unit cell in magic graphene. So as I mentioned before, so the size of the unit cell is around 15 nanometers. And therefore, calculations by Leonid showed also that if you bring the graphite gate closer than 15 nanometers to the magic graphene, then screening effects should be large. And here is really a calculation by Leonid where he calculated U as a function of distance of the graphite gate. And indeed, really, he predicts that below 30 nanometers, and in particular with like critical length scale of 15 nanometers, U can dramatically be quenched. And so we did the experiment. So we fabricated several devices, and all these devices have slightly different twist angle. So and also they have slightly different distances from the graphite gate to the graphene gate. And so this device here, this has device 3. This shows all the characteristics which are typical for the devices. It shows strong correlated insulators and superconductors. And this device is exactly dead on magic angle, so it has a very small T. And the dielectric thickness here is not so small. It's in the orders of 15 nanometers. And here we really observe these strong correlated insulators. But in the top two devices, you can see that actually the correlated insulators disappear. So for example, for this device here at -2, we don't see any trace of a red region. So the resistances are really low here. We don't see a correlated insulator. However, at the same time, while the insulators disappear, the superconductors don't disappear. So this superconducting state, it really resides here somewhere close to the center of the band, and with a TC which is comparable to the TC of devices with correlated insulators. And most drastically here in this device with also slightly larger twist angle and even thinner, even closer proximity to the graphite gate, it really has this broad superconducting region, which is not interrupted by a correlated insulator. And so I think with this study, we kind of have shown that in principle, if you weaken the correlated, so I think to summarize, so we have shown that you can weaken the correlated insulators by this dielectric screening effect and by tuning the twist angle. And at the same time, while we have observed that the correlated insulators start disappearing at a rather quick rate, the superconductors remain relatively strong with TCs which are comparable to the devices which are unscreened. I've seen there was a raising hand, right?
Yes, and actually it transformed into a direct question, but I can, I think, Till, you can unmute yourself probably and ask the question if you want.
Yeah, I can also ask it at the end, but there's just this notion that where you mention this carrier density, and then you say that this is the lowest carrier density superconductor and still has a very high TC. But I don't see, I actually don't know any law which relates the TC to the carrier density. Do you?
Yeah. So this was actually right. So okay. So this is not a law, I think, but I think if you look at all the typical superconductors, and this is also worked out in Pablo's original paper, so this was worked out in the Uemura plot. So typically for all DCS superconductors, if you compare TC versus TF, it's relatively low. It's much lower, for example, than in the COOP rates. And usually this type of plots was used to sort of distinguish sort of unconventional superconductors with strong coupling versus conventional ones.
So if I may continue on the same topic, isn't this actually a law in the sense of DCS theory, because the DC is directly proportional to the Fermi level, and that is somehow related to
yeah. Right. So I think in the Macmillan formula, if you calculate the TC, the density of states is in the exponent, and therefore.
Yeah, but this is based. Macmillan formula is based on an assumption of a Fermi surface. It's a finite Fermi energy. You have a flat band, so you should not use Macmillan formula.
Well, but if it's a two-dimensional superconductor, Castor-Stalis relates TC to the density of electrons in the superconductor.
Yes, and no, but there is in between there is a delta, which actually, so the density of the Castor-Stalis temperature is actually proportional to superfluid weight. The superfluid weight is proportional to the delta times the density, right? Okay, in the usual case. So that means that the TC and the density is still not related.
Okay.
Okay.
Shall we continue there, or I see that those who asked the questions muted themselves already again. So maybe we continue, and if there are questions later, we can continue there.
Okay. And right. So and I want to just a little bit summarize the results. So we also published recently a review on these topics together with Andrea Young, Corey Dean, and Leon Ballance. And so basically we tried to look at all the different reported phase diagrams in twisted bilayer graphene with superconducting phases. And really what I think these two graphs kind of try to summarize this. So first of all, what you can see is there were not too many superconducting devices reported in literature. So I think by the writing of the review, there were 8 devices reported. By now, I think you can find maybe 15 to 20 devices reported. I think what clearly was observed by the early studies is that usually the superconductors were found close to correlated insulators. However, several recent studies, including ourselves, but also Andrea Young and Stefan Nachberge, they found also that in devices without any pronounced insulators, but really with metallic regions close to half filling, you also still can observe superconducting regions. And maybe the other take-home message is here, if you look at all these different phase diagrams, you can see that somehow they all look slightly different, where superconductors kind of appear clustered maybe to close positions to the band centers, but they're really not entirely at the same place. So I think one of the things one can really see here is that we probably still have some, we're still fighting disorder in the system, and really we are still every device behaves slightly different. And I think one way to think about it, at least I think about it this way, is that maybe this is like some sort of really still very mesoscopic type of system, where really small disorder profiles can change really the subtle effects here. However, I think it's really superconductivity is a really robust phase here, which is observed in many devices. However, exactly in the exact details of the phase diagram are still a little bit disordered. Okay, so next I want to end the topic of superconductivity, and I really want to talk about topology, and Ali will talk in much more detail about it. So I'll really try to cover only 10 minutes of this. And so this is really recent work, which was first introduced by Ali Yazdani's STM work, but then there were several other groups which followed in the footsteps, in particular Andrea Young, ourselves, Nachberge, Eva Andre, also Pablo Carlo Herrera had a paper on capacitance measurements, I think, of these type of things. And so what we really started seeing in all of these experiments is that we see really well-defined regions of quantized Hall resistance, which typically persist down to zero field. So as I will show later on, so we had really observed quantized Hall resistances down to 0.3 Tesla, but now actually we have also results on the zero field. And these regions can be summarized in this measurement here. So this is, again, a resistance measurement as a function of a perpendicular magnetic field and as a function of filling factor in the system. And you can see sort of by the slope that originating from the charge neutrality point with filling factor 0, we observe this region of Rxx equals 0 and Rxy quantized to 4e squared over h, which is basically marking this Hall state with Chern number 4. And really this state, as you can see, this originates almost at 1 Tesla. Then starting from filling factor 1, we observe this region with quantized Hall conductors of Chern number 3, from 2, Chern number 2, from filling factor 3, Chern number 1. And really, we observe this, really there is a well-defined correspondence of these states with respect to filling factor and the Chern number which accompanies it. So these is really the sequence which is very robust. And if we now take many devices which we have measured over the last year, then really we can really see that these Hall conductance regions, they're really in almost all devices we measure. And if we summarize them, this sequence is really robust. With some with these data points which I'm showing here, they're marking the onset of the quantization, and you can see so some of the devices have extremely low quantization values. So this one here, this Chern number -2 from filling factor -2. This was so far the lowest, and it really had an onset of 0.3 Tesla. And the other thing, of course, which raises immediately the question is whether these states can persist down to zero field. Then, of course, one raises the questions: what happens to the superconductivity? Or, in other words, do we have to think now about the superconductivity on top of these topological states? And could the superconductivity, which we observe in all of these devices, could this really have also some sort of topological superconducting properties? Okay, so and basically, without going too much into detail, because I'm sure the next speaker will cover it in much better detail than I do here. But basically, the ongoing theory which was again developed predominantly by people like Andrei Bernovic, Ashim Vishnavan, Al McDonald, and many others, is that really we need to think about the Moiré flat bands as topologically non-trivial bands. And because we have, in principle, 8 flat bands, we can actually think of them as 4 flat bands with Chern number 1 and 4 flat bands with Chern number -1. And then, but these bands are degenerate typically. However, when we cool the system down and interactions become relatively strong, then these interactions can start breaking C2 or time reversal symmetries. And these interactions therefore open gaps between those Chern bands, and they really reveal these non-trivial gaps, which then have the associated Chern numbers and quantized Hall conductances. And without going into detail, so a big ingredient of this whole story is, of course, valley symmetry breaking, which can be induced by C2T symmetry breakings. And the general idea is that, for example, here in the state of charge neutrality, we can treat it as 4 occupied bands of Chern number 1 and 4 unoccupied bands of Chern number 1, which gives us this overall Chern number of 4. However, if we start filling now the system and we go to the filling of 1 electron per unit cell, then we actually fill only one of these bands at a time, and therefore we get valley symmetry breaking here, and we fill only one band in the valley with Chern number -1, which then results in a Chern number of 3. And one can actually then repeat this argument for all the other states and also all connectors. So with this, I think I'm close to wrapping up, or do I actually still have time?
Well, since there were questions in between, I think you can go on.
Oh, so I can go. Okay, then.
5
all right.
minutes or so.
Okay, good. Then the other thing I wanted to mention is that really we also followed a theory by Andrei Bernovic, and he actually also asked himself the question, what are the other signatures of these topological flat bands? Because actually originally we didn't see these quantized states so well. And Andrei basically started to postulate that really the Hofstadter spectrum, so basically the Landau levels and high magnetic field in these topologically non-trivial bands should behave very differently than in a trivial non-topological system. And so basically, the idea is really that if we now look at the Hofstadter spectrum of a trivial system, so this diagram basically shows 2 bands which are separated by a trivial band gap. And if we apply magnetic field in this direction, really what happens is that all the Landau levels within each band, they're directed inwards towards the center of the band, and they really disperse inwards of the band itself. Therefore, if one looks at such a phase diagram, one can really easily show that that the Hofstadter spectrum is always confined to the underlying bandwidth of the original band, and all the Landau levels are confined within it. Therefore, if one has now 2 bands which are separated by a trivial gap between one another, this gap can never be closed. And this gap really always remains in place, and this gap cannot be bridged in no way. And so what Andrei showed in his, there are several theory papers from last year, is really that in a topologically non-trivial bands, this doesn't hold true anymore. And the Landau levels within each band, they're not confined anymore to their energy, but they can disperse outwards of the band. And so this is shown here, for example. So this is the bandwidth of this band at zero magnetic field. As you can see, if you increase the field, some of these bands freely disperse outside of the band, and therefore they can bridge any type of trivial band gap in the system. And basically, the clear experimental observable would be here that you are closing trivial band gaps in the Hofstadter spectrum. And so basically, for this type of experiment, what we did is we actually made devices of twisted bilayer graphene with the second magic angle. So the second magic angle is basically the second angle where the bands become very flat. So if you can see this here in this sort of plot which I made before. So here, the first magic angle is here where the bands become really flat for the first time. But then the second magic angle is an angle which is lower than the first, where there is a second position where the bands become flat again. And typically this is in the order of 0.5 degrees. And we have, so this was calculations done by Andre and by Alan McDonald. We have really looked at the spectrum of these magic angle graphene close to the second magic angle. And you can really show that this system can be described by 10 relatively flat bands. And these bands are mostly non-overlapping. So actually, this non-overlapping feature of these bands is really due to the interactions in the system. So interactions kind of like to separate the bands out. And you can see, so we can really obtain this complicated system of 10 flat bands. They're either slightly gapped between one another, or they're touching with each other by Dirac points. And so we made the devices and we did the measurements. And so what we see here is a typical resistance measurement of a close to a second magic angle device. And what we see really dramatically with a measure RXX as a function of carrier density is we see that we see 10 very sharp resistance peaks. And if we look now at the distance in carrier density between those two peaks, and we can show that the distance between two peaks is just the carrier density you need to fill one band fully. So therefore, those are fulfilling positions of the individual bands. And our understanding is that these points here, these high resistance points, they're really just transitions in between the bands. So whenever we go from one band to another, we cross like a point of high resistance. And this is really an analogy to these band gaps or these Dirac points, which we see. And we are basically, every time we see resistance peaks, we're somewhere in between two bands. And of course, Hall measurements also demonstrate a similar thing. So Hall measurements also show transitions every time we cross one of these peak positions. So we really can show that we're we are basically filling up one band and going to the next. And so the interesting part is now the high field data. So really, if we go to high fields in these small twist angle devices, we reach one flux per unit cell relatively quickly. Approximately at 4 Tesla, we already reach 1 flux per quanta, 1 flux per unit cell, and at 8 Tesla, we're about 2 flux quanta per unit cell. So basically, we have all the conditions in place to observe the Hofstadter spectrum. And really, if we now look at this typical Hofstadter, we really can see that at high fields, we really see well quantized conductance regions, which are developing in this non-monotonic way, just as was shown previously in Hofstadter spectrum on graphene on HPN. And most strikingly, we can now start to analyze the spectrum, where we see these most dominantly these red regions, which are the trivial band gaps between the different bands, which I showed before. So these trivial band gaps, they don't have a slope in the magnetic field phase diagram, but they just go as straight lines. So each of these red lines basically marks the interband transition from one band to another. And most strikingly, we really see whole states which can cross these integer these trivial band gaps. And really, to summarize this kind of crisscrossing pattern, we can zoom in at really the center region where we really see quantized whole states which originate from different bands, crossing freely between many different bands. And this is really in agreement with the prediction by Andre, and also in agreement with the calculations they made. And really, this, to our understanding, is a new type of Hofstadter spectrum, which is unbound as compared to the previous ones. And this really showcases how Hofstadter spectrum has to look like if the underlying system is topological. Okay, I think with this, I'm gonna start wrapping up. So I think I want just to summarize a little bit that really, I think everybody who is in this field right now is pretty excited because we now have all these possibilities. We have correlated insulators, superconductors, magnets, and topological states in one material platforms. Many groups have now also gone down the path to study different combinations of different materials that have shown similar physics. So not just twisted bilayer graphene, but also ABC trilayer graphene shows some of these same phenomenology. Also twisted stacks of two-dimensional semiconductors like WSC2 or MOS2, which was shown by the group of Corey Dean and Philip Kim. And in principle, I think many other groups, they're now trying to take many of the two-dimensional materials from the family of Van der Waals materials, and they're trying to twist them with respect to one another. And I think the following years will show a little bit more of discoveries of novel quantum phases. And I think in particular, one of the key directions will be to somehow create systems with ever bigger interaction energies, and hopefully also with ever bigger critical temperatures. So with this, I want to thank my group again, and I want to thank you for your attention.